next talk by John Readey on HDF for a Cloud HSDS server. John, do you want to share your screen?
Yes. Let me get started here. Okay. So I'm sharing, and let me get my slides.
Yes. Can see your screen.
Okay.
Slides are on. Yes. Go ahead, please.
All right. Thanks. So I'm going to be talking about HSDS, which we've heard about a bit. It's the REST server for HDF5 data. Overview, I'm going to talk about why an HDF service, what's REST, some HSDS features, overview of the architecture, how security works within the cloud context, and possibly a demo if I have time. I want to say, yesterday I talked briefly about H5PyD, which is our Python client for a server. And tomorrow I'll be talking about the RESTful, which is the HDF5 library plugin. So in effect, a C client for a server. So be sure to catch those talks. So HSDS, it's a REST-based web service for HDF data. When we started this, our criteria was have really good performance, be highly scalable, as the name implies. Meaning that we should be able to run it with any number of clients, any amount of data, any amount of throughput. And feature complete. We want to support most, at least, of the features provided by the HDF5 library. And we want to be able to, initially the goal was for object storage, specifically AWS S3, but recently this has been expanded to support Azure Blob Storage and POSIX file storage. This was originally funded by NASA as part of the NASA Access 2015. HSDS Platforms. So the service is implemented using containers. And maybe Docker was the first platform to run containers, but then there's Kubernetes, there's Amazon EKS, which is like a managed Kubernetes. There's Azure Kubernetes Service, which is the Azure version of managed Kubernetes. There's DC OS, which is a Mesos OS type of system. So a lot of different platforms to run containers. And the nice thing with our architecture is the core code works through all these platforms. And the only changes like around the edges in terms of how you, say, spawn new containers and such. Likewise, as I mentioned, the data is stored either on POSIX or S3 or Azure. And there's also a fair number of on-prem object storage systems like OpenIO and Ceph that can be used as well. So here's my long list of HSDS features. Let me run through these. So features that apply to what HDF5 does as core functionality. So we have groups, links, including multi-links, i.e. like two links that point to the same object, attributes, data sets, committed data types, simple and compound data types, hyperslab and point selections. And there's also, this is not a feature in the HDF5 library currently, but we support SQL style queries across compound type data sets. We support compression, not only the standard HDF5 compression filters, but all the BLAS compression filters. Quincy was talking about the challenges with variable length data. So one nice feature we have is that we support compression for variable length data sets, which isn't supported in the HDF5 library. As I was saying, it's container-based and scalable. So one aspect of scalability is that we can cache recently accessed data in RAM. So the HDF5 library has metadata caches and chunk caches. But the nice thing in the server context is that you can have cache that's multi-gigabytes in size that's shared by all the clients to the server. And that cache, since a lot of times your storage system is quite slow to access compared to a local disk, that can really speed up performance. As we'll see, we parallelize requests across multiple nodes. So not only do we parallelize multiple clients making requests simultaneously, we can parallelize individual requests to a server. And this works by having each chunk of data run on a separate container. And then those results get amalgamated back. You can have a knob to improve performance by just instantiating more nodes. If you're running on a cluster-based system like Kubernetes, those nodes can be running across a set of machines. We support not only single writer, multiple reader, but multiple writer, multiple reader. And there's no limit to the amount of data that can be stored. So we've had customers with hundreds of terabytes of data. Maybe that's small still from the history of HDF, but it's a good start, I think. But let's step back and say, well, why have a service at all? So a few motivating reasons. It allows remote access. So when you have really large data sets, that moving that data to where you are can be quite expensive, both in dollars and in time. By having your requests go to the data, that can be much more efficient. Also, it's a language neutral interface to HDF. So in the cloud world, when you say API, usually you mean a REST API. And by its nature, it doesn't matter what language the client is using. So it's kind of an interface that can work with any type of client host language. It enables web-based applications, right? So as far as I know, there's no way to have a web page make calls to the HDF5 library, but that's very natural for a REST API. It facilitates container-based applications, right? So containers can not only be used for the server itself, but for the application. And again, in the cloud context, having files is at best problematic, right? Most cloud deployments prefer to have microservice architecture where one container is reading from a service and writing to another service. And here, HSDS fits very nicely in that paradigm. This is I think it's a good platform, again, referring to some things Quincy was talking about, to experiment in alternative ways of doing things, right? Whereas with the library, it can be quite a challenge to try out new features. It's a little bit easier with HSDS. Okay, so let's talk about REST. So REST is a loose standard for creating web-based APIs. Okay, it's not necessarily, but typically uses HTTP, and for typical HTTP operations of get, post, put, delete. It's stateless. All right, but what I mean is that one operation doesn't refer to previous operations. This is opposed, for example, to say RPC-based implementations or the HDF5 library itself, whereas when you are making an HDF5 call, those calls you made before matter, right, into the result of that call. By contrast with REST, the request stands alone, right? It does what it does, and doesn't matter what came before or after. And it also doesn't matter what particular container you're talking to, right? So when you have multiple containers, one request may go to container A, and the next request may go to container B, and the client will be unaware, typically, of that. URI based, so every object has a unique identifier. So every data set, every group, every chunk has its own GUID to refer to it. And I was saying that it's language neutral. So over time, and it's been a process of 6 or 7 years now, we've defined a REST API, which enables the HDF data model through REST. It's used by HSDS and also H5 Serve, which was an earlier prototype project we did. But other implementations are free to adopt it as well, right? And by adopting it, you're enabling any application or web app that uses the REST API to work with that adoption. So here's a tongue-in-cheek, the simple diagram of the REST API that Gerd Heber came up with. So it's you imagine trying to fit the entire HDF5 API into get, put, post, delete is its challenge, but we've worked out the schema to do so. And why is it RESTful? There are these 4 methods, and there's certain assumptions that developers will have on how those methods behave. For example, get is safe in that it shouldn't change data, and it's idempotent in that you can make the same get request repeatedly, and you'll get the same result. Again, for RPC, usually RPC protocols are implemented as get, but they're not safe and they're not necessarily idempotent. So by following these kind of standards, it works better with people's expectations of how REST APIs work. Here is an example of what the HDF REST URI might look like. So you've seen this countless times when you've been using a browser or something else. You have a schema like HTTP or HTTPS. The endpoint, that's the DNS name of the server you're talking to. The port, if it's not port 80 or port 243 for HTTPS. And then the resource. So here, the resource is, in this case, data sets, referring to a data set, and then the GUID. And then, so now I'm talking to a particular data set. And in this case, I want to get the value for that data set. And I suppose maybe the shape or the type. And I want not all the values, I want to get this 4x4 block of values, right? So this is what I mean by it's stateless, right? It doesn't matter what previous conversations I had with the server. If this request comes in, I'm going to get this defined result back. The response can either be JSON, which is typically used for metadata. So if I want to get, say, the shape of the data set, I'll get a JSON response back. But that's not very efficient for large data reads. So we support getting binary responses back. All right. So if I'm reading, 10 megabytes of data, I would typically want that back as a binary blob. Okay. So next, let me talk about the architecture. So I mentioned it's containers, and there are 2 types of containers used by the HSDS: service nodes and data nodes. Okay, the service nodes are the endpoints of the client. So a request comes from the client. It may go through a load balancer and land up on any one of these service nodes. The service node will authenticate the request, verify that the client can do what he wants to do, and then it will pass on a request to one or more data nodes. The data nodes in green, they are the containers that actually read and write data. And they're reading and writing to either a POSIX store or an object store. And there is this virtual partition of the object store space, right? So you imagine all the objects, right? All the data sets, all the groups, all the chunks living in this object store space. And there is a partitioning algorithm, so we can randomize which partition a given object will live in. And each data node owns a particular partition. Okay, and we can vary dynamically the number of partitions and number of data nodes. So you can have 4, you can have 1, you can have 100. When a request for, say, a Hybris Lab selection comes in, each data node will get a request to read one chunk. And that's where the parallelism comes in. Let me show you this one. In this diagram, we represent a data set. The heavy lines are the chunks. And a client may want to read this yellow rectangle. It covers 6 chunks. So that request would come to a service node. The service node would make 6 requests to whatever data nodes are present. And each data node would read its part of its assigned chunk. When that's done, the result goes back to the service node. The service node puts together all those responses and returns it back to the client. Hence, we get some speed up, right? The more nodes you have, the faster some operations will perform. My intent wasn't to talk about the clients much here, but I should say that not everyone wants to write using this REST API. I may have existing C applications or Python applications I like to use, and hence we support these client libraries. So yesterday I talked about H5PyD. So I have a Python application that uses H5Py. It's very easy to switch that to H5PyD. H5PyD will convert those API calls to REST calls to a service and back. Same thing for the RESTful. Your existing C applications can just magically use RESTful and be talking to a server rather than local files. A word about Python. So for high performance people, Python may seem a bit of an oxymoron as a language to write a server in. But you know, it's worked pretty well for us. So even though Python doesn't support true multi-threading, because we use Python packages like BLASK or NumPy, which are highly optimized code, it works pretty well, right? Because most of your time are spent calling these other packages. We also use Numba, which is a JIT compiler for Python that gives you typically like 100 times speed up for things. And we use asyncio, which makes very efficient use of CPU for IO-bound applications. So let me talk about async IO. So rather than multi-threading, we use task-based concurrency on the server. And it works like this, right? You have a function, you're doing some regular stuff, and then I want to call something that may take some while to come back. It's going off to a server somewhere. So you decorate your function with async, and when you get to the long call, you say await. And what this does is that your program will switch to another task until that blocking call returns. So if it's like, say, read some bytes from S3, you can be going off and doing other useful things. And when that S3 call finally returns, you'll just resume this code. So it works very well, and it greatly simplifies a lot of the issues we have with data structure protection and such, right? Because there's only one process, only one thread. So any given code, you're only doing that one thing, but yet we can multitask over thousands of potential concurrent tasks. Here's an example of how you do something like reading multiple chunks. So I have a list of chunk IDs, say, and I say this async IO ensure future for each chunk ID. So we loop through this, and you append to this list of tasks. And then you say await async IO.gather all my tasks. And what that does is that it will run each of those tasks asynchronously. When they're all done, your code resumes, right? So if I need to read 100 chunks, I'll just go away and do other stuff. And once those 100 chunks are read, I resume my code execution. Lastly, let me talk about security. Quite important in the web context. I guess it's important for everyone nowadays. Every request that comes in needs to be authenticated. And there's several protocols that HSDS supports for authentication. The simplest is HTTP basic auth, where the username and password is encoded in each request. We also support Azure Active Directory and Google OpenID, which are third-party style. So it's not the server authenticating user identity, it's some open identity service that's doing that for us. Once we've authenticated the user, we want to authorize, right? So I may know that Quincy has made this request, but does Quincy have permission to, say, delete my file or not? Well, let's check. The access control list is associated with each domain, equivalent to the file. And it's a list of users and what actions they can perform. Can they read, can they update, can they delete, and so on. If you want to provide access control, say, for a large group of users, you can use role-based access control, which you define a group of users, and then you apply that group identity to the actions they can perform. All right.
John, we're almost
over time. Yeah, so that's all I had, actually. And then here's some links to various GitHub repos if anyone wants to try things out.